Hello, this is Dr. Stutzman, and this is our first video of Calculus 2, partial fractions, which is a technique to help us find some antiderivatives uh, where this doesn't match any of the rules. We can't use U substitution. But if I knew that this fraction was the same as 1 over x plus 1 minus 1 over x plus 2, then I can use U substitution rule, to find, and the log rules to find those antiderivatives. Because if u equal x plus 1, knowing that the integral of 1 over u du is natural log of u, and the derivative of u is the same as derivative of x, then I can just get natural log of x plus 1 minus natural log of x plus 2 plus c. Now, let's see where we came from. So here is a integral where u substitution does work, because if we look at the denominator, its derivative or something like it, there's a multiple of it, is in the numerator. So if u equals x squared minus x squared plus 2x minus 3, the derivative of u is 2x plus 2, which is 2 times our numerator, which is x plus 1. So I can do my substitution and get 1/2 natural log of u and plug things in. Now, let's see what happens if we don't have, because if this was not x plus 1, but it's something a little bit different, like x plus 7, then our substitution doesn't work. So how do we get there? Well, back when you were in middle school or in algebra, you learned how to add fractions and combine them together into a single fraction. Well, we're going to work in reverse. So given that exact equivalence, how can I go from a fraction into separate fractions, which then I can then find the, if I knew that x plus 7 over x squared plus 2x minus 3 is equal to these two fractions added together, then I can find the antiderivative of each one separately, because the integral of a sum is equal to the sum of the integrals, and get what we have here. Well, how do we find those fractions? Well, we're going to use technique called partial fraction decomposition, where if you have a rational function where the denominator has a larger degree than the numerator, and I can factor the denominator into a bunch of linear terms, for example, like x plus 2 times 2x minus 1, and keep factoring until I get to the nth degree, then I can rewrite this rational expression as a sum of fractions where the denominator is each of the factors, and the numerator is just a constant. And our objective is, how are we going to find out what this constant, how are we going to find these constants? So what we're going to do is take our, what we're trying to trying to find out x plus 7 over x squared plus 2x minus 3. I know that it factors into x minus 1 times x plus 3. So I've got that equivalent, and the way I'm going to find it is, first I'm going to multiply both sides by the denominator. Multiply the left side by the denominator, multiply the right side by the denominator, but I'm going to write it in factored form. Well, the left side, the x plus 2 minus 3's cancel out, and I'm left with just x plus 7. The right side, if I distribute, multiply that by a over x minus 1, the x minus 1's cancel out, and I'm left with just a times x plus 3. And similarly, the b will be multiplied by x minus 1. Well, this equation is important, and I'm just put a star next to it because I'm going to use it a number of times. Now, our objective is, what do we have to find out what a and b are? Well, if they're true for any value of x, it's equivalent. I'm going to pick what values of x I want. I can pick 0 and 2, but that would give me a system of equations. So I'm going to make it a little bit easier. I'm going to pick a value that make it really easy to solve. I'm going to let x equal -3, which seems like an odd choice, but if I put -3 in for x, then this first term is going to disappear. So if I plug x equals -3, I get -3 plus 7, which is 4, is a times -3 plus 3, plus b times -3 minus 1. That disappears. I get 4 is equal to b times -4, or b is equal to -1. I'll remember that. Let's pick another value of x. Well, let's pick a value of x such that this term will disappear. Well, if I pick x equals 1, I'll make that disappear so I can find out what a is. So let x equals 1. I get 1 plus 7, which is 8, equal to a times 1 plus 3, plus b times 1 minus 1, which is 0, so that disappears. I get 8 is equal to 4a, or a is equal to 2, which now I know that my x plus 7 over x squared plus 2x minus 3 is exactly the same as a, which is 2 over x minus 1, plus b, which is -1 over x plus 3. Now, this technique worked when I only had when my denominator was a larger degree than the numerator and I didn't have any repeated terms. If my denominator was a smaller degree than the numerator, then I'm going to have to do some long division to find a polynomial quotient plus a remainder, and the remainder is going to be, by definition, the remainder will have a denominator of larger degree than the numerator. And I can use the same technique to find what that decomposes into. Some things we're not going to do in this video is what happened if I have repeated factors. For example, this denominator, x squared plus 2x plus 1, is equal to x plus 1 squared, and it repeats by a power of 2. Well, that's going to, the way we we decompose it, we can write each of the repeated factors to the first power and to the second power until I get to whatever power it was. Another thing we're not going to get to in this video is if you have quadratic factors, which means I get one factor like x squared plus x plus 1, which doesn't factor over the reals. So I can just leave it as it is. And I put it as, instead of just having a single constant, I have a constant times x plus an additional constant. Let's do a couple examples. So I've got a second degree denominator, and we're going to write that. We're going to say, well, that's the same as x squared minus x minus 2 factors into x minus 2 and x plus 1. Now, if you didn't do your if you didn't do x minus 2 first, you did x plus 1 first, you'll have different letters in front of them, but you'll get the same values when we're all done. Well, first thing we're going to do is, after we set this equivalent, multiply both sides by the denominator, which is x squared minus x plus 2. If I multiply by that, I get 5x minus 4, which is all left, is equal to a times x plus 1. Notice that that's not the same. So if I multiply this by x minus 2 times x plus 1, the x minus 2's cancel out, and I'm left with just x plus 1 plus b times x minus 2. Put a star next to it because I'm going to use it a number of times. Let's find out what a and b are. Pick convenient values of x. Let x equals -1. So 5 times -1 minus 4, which is -9. It's equal to a times -1 plus 1, which is 0, plus b times -1 minus 2. So I get -9 is equal to -3b, where b is equal to 3. Pick another value of x, let's say 2. So I know that's going to let another thing become 0. So plug it into my star equation, 5 times 2 minus 4, which is 10 minus 4, which is 6. Is equal to a times 2 plus 1, plus b times 2 minus 2. That disappears. So I get 6 is equal to 3a, or a is equal to 2. So now I can plug my a and b's in and get my original antiderivative, my original indefinite integral is equal to the integral of 2 over x minus 2 plus 3 over x plus 1. Find the antiderivative of each one separately. So I get 2 times the natural log of x minus 2, which works because if u is equal to x minus 2, then du is the same as dx, plus 3 times the natural log of x plus 1 plus c. All right, let's do another one where we have more than two factors. We factor the denominator. I get 13x minus 6 over x cubed plus x squared minus 6x is the same as 13x minus 6 over, I can factor an x out. I'm left with x squared plus x minus 6, which factors into x plus 3 times x minus 2, which can write each of the factors by themselves in the denominator. And pick constants to put in front that to solve for. All right, multiply both sides by the denominator, and I get the left side is 13x minus 6. The right side, after I distribute, I get the x's cancel out. I'm left with an a times the other factors, which is x plus 3 times x minus 2, plus b. The x plus 3's cancel out. I'm left with x times x minus 2. And the last one, c times the other factors, which are x and x plus 3. Pick convenient values that let things become 0. Well, if I let x equal 0, then I get 13 times 0 minus 6, which is just negative 6. A times 0 plus 3 times 0 minus 2 plus b times 0, 0 minus 2, that all disappears. C times 0, 0 plus 3, that all disappears. I get negative 6 is equal to negative 6a, or a is equal to 1. We'll remember that. Let's pick another value. Well, if I put x equals 2, then I know the x minus 2's will disappear. So I get 13. Don't forget to plug it into the left side. 13 times 2 minus 6, which is 26 minus 6, which is 20. Is equal to a times 2 plus 3 times 2 minus 2. That will disappear. Plus b times 2 times 2 minus 2. That will disappear. Plus c times 2 times 2 plus 3. So I get 20 is equal to 2 times 2 plus 3 is 10. 10c, or c is equal to 2. Pick another value, and I would let x equal negative 3. That'll give me my last one disappears. Get 13 times negative 3 minus 6, which is negative 39 minus 6, or negative 45. Go to a times negative 3 plus 3 times something that's going to disappear, plus b times negative 3 times negative 3 minus 2, which is negative 5, plus c times negative 3 times 0, that will disappear. So I get negative 45 is equal to negative 3 times negative 5 is 15, 15c, or b is equal to negative 3. So I can plug all my constants back in, and I get the antiderivative of 1 over x plus b, which is negative 3 over x plus 3, plus c, which is 2 over x minus 2 dx. Find each of the antiderivatives separately, because this antiderivative of a sum, you want natural log of x, minus 3 natural log of x plus 3 plus 2 times natural log of x minus 2 plus c. All right. Next one we're going to do is when we have an improper fraction where the degree of the numerator is smaller than the degree of the numerator is larger than the degree of the denominator. So I'm going to do some long division to make it so that I have a remainder which is a proper fraction. Well, my divisor is x squared minus 1. I'm going to divide that into x cubed, leave a space for my x squared plus x. Now I'm thinking, what does x squared multiply to give me x cubed? I need to multiply by x. Multiply my divisor by x, I get x cubed minus x. Subtract that divisor, and I get the x cubes cancel out. X minus a negative x is 2x. And I have nothing else to bring down. And 2x has a smaller degree than the numerator, so my remainder is 2x divided by my divisor, x squared minus 1. So now I have, it's the same as the integral of my quotient, which is x, plus 2x over x squared minus 1. Now I'm going to have to do something to find out what that antiderivative is. You may be able to use u substitution. Actually, you can, but I'm going to use partial fraction decomposition. That's x. Let's figure out what 2x over x squared minus 1 is 2x over that difference of two squares, x plus 1 times x minus 1, or some constant over one of my factors plus another constant over my other factor. Multiply both sides by my denominator. I'm left with 2x on the left. Multiply, I'm left with a times x minus, it should be an x minus 1. X minus 1 plus b times x plus 1. Plug in convenient values. Let's plug in x equals 1. I get 2 times 1, which is 2, is equal to a times 0, plus b times 1 plus 1, which is 2. So I get b is equal to 1. Let x equal negative 1. I get 2 times negative 1, which is negative 2, is equal to a times negative 1 minus 1, plus b times negative 1 plus 1. That disappears. I get negative 2 is equal to negative 2a, or a is equal to 1 also. So I can rewrite my integrand as the integral of x plus 1 over x plus 1 plus 1 over x minus 1. Find the antiderivative of each separately. Use my power rule for the x. It's 1/2 x squared plus natural log of x plus 1 plus 1 times natural log of x minus 1. Let's see. I'm going to leave one for you to do. This one, you're going to have to, it's a proper fraction, so we're not going to have to do long division, but you're going to have to find out first, you have to remember how to factor the denominator. So it's going to factor into 2x and x plus or minus something. And be careful when you find the antiderivative, and then when the antiderivatives, because the antiderivative of something that the leading coefficient is not 1, you have to do some u substitution, and you should get this as your answer. All right, see you next time.